So hi everybody. I am Rubens. I am a student of Politécnico of Turin. I did the internship here at the research center at RAI, and I worked on the optimization for mobile reception at the receiver side of. Alessandro will speak something about.
Yeah, just a very quick introduction of the reason of this work. Here in Italy, we have two active 5G broadcast transmitter, one in Turin and one in Rome. And in the future, we plan to switch on more transmitter on high populated cities. And so we on all city, when we switch on a transmitter, we try to understand what is the coverage and what we can do with this signal. And we do a lot of tests pedestrian, so with the smartphone handheld, and we do a lot of tests in car, receiving the 5G broadcast signal in car. And we note that the 5G mag reference tool has some problem, not related to the tool, but specifically to the library that do the modulation of the signal when we are in a mobile environment. And so from this little problem, we start with a thesis project held by Rubens.
Okay. Introduction is, well, I worked on a low section of the modem block at the receiver side. So the modem itself receives the signal via a software-defined radio device, and the focus of the project was the optimization of conversion from the symbols of the receiver to LLR bits, so log likelihood ratio bits. We take the channel estimation and the symbol equalization as they are done in separate blocks. So we take these and we work with these to optimize the log likelihood ratio bits. So the initial issue is that for mobility and bad channels, which on the left we can see a frequency band that has a lot of holes, which they are in self echoes in, for example, urban scenarios, and this is a sort of exaggerated the signal in which the signal is very bad in these sections. It's echoes of 1 decibel, so which is very low, and echoes of 1 microsecond, and which, as I was speaking, was the figure on the left is channel estimation, and on the right we can see the log likelihood ratio bits, which are the demodulated bits that are the most important. Here we can see that in parallel, where the channel is very bad, which has a lot of holes, we can see that the bits, there are some outliers, points that we're not sure that what they produce. So they produce errors in the signal or in the bits received. What some broadcast receivers do, which we implemented as well, is that the channel estimation block, which estimates the response of the channel, we use it with a feed-forward manner, squared, and taking the absolute value of it to fix this issue that arises where the outliers of log likelihood ratio bits happens, so that we can nullify this uncertainty. Okay, this is a pseudocode, so sort of simplified simplified version of what is done. So in short, for each symbol that is received, we find the state of the channel estimation for two floats. So a symbol that is received has a real part and imaginary part due to the modulation scheme that is used. And also the channel estimation also has a real part and imaginary part from the channel estimation block. And we take the channel estimation for each respective symbol, we square it, we take the absolute value of it and square it. And then for each log likelihood ratio that comes out of this of each symbol, we multiply to the respective channel estimation absolute value squared, and then we append. So the output is this multiplication. I will go shortly on a topic that that the code is written on. It's parallel processing. There's a process, a computer architecture process, which is called SIMD, so single instruction multiple data, which allows to process 4 values at once. This is a very low level part of method of doing the computation. It makes it faster and optimizes the processing of computation. And since this is a very low level method of processing, it also takes into account the processors in which the code is being ran on. So, for example, there is devices like Intel or AMD, which use this SIMD process, and it uses libraries that are called SSE, and respectively for ARM devices that are, for example, mobile phones or Raspberry Pi in our case that we use. It uses libraries that are called Neon V8. And the code that is modified is written for both of these cases. It's basically the same concept, it's just different names for the functions. And okay, so this was said because the process of doing this multiplication is done in this vectorized manner. So simplified log likelihood ratio for this is only for 16 QAM. It's also done for 64 QAM. It's the same principle. It's just different values of offset, which I will explain shortly. So a symbol that is received is composed of a real part and imaginary part. And in 16 QAM, we get 4 bits, which in log likelihood ratio, there is a very high complexity process to compute this, but in computer, how the code is written is that it's simplified and it uses a very similar result, and which is very faster to compute. We can see on the second block here that the first bit we get the negative part of the real part of this symbol received. For the second bit, we get the negative part of the imaginary. For the third, we have the absolute value of the real part minus an offset, which is a constant of 16 QAM. Also, for the fourth bit, it's the absolute part of the imaginary minus this offset. So what the modification that we wanted to do is that multiplication of the real part of each log likelihood ratio to this channel estimation absolute value squared. And since we can see for the first and the second, it's just a simple multiplication. For the third and the fourth, where there is an offset constant, we have to multiply this channel estimation absolute value squared to both the real part and offset separately. This doing it separately is due to the fact that the code was written appending both of the 4 elements into a vector of 8 elements in a different floating point manner, and that's the only reason that they're done separately. And I will explain now how it is done shortly. So in the right, where the green blocks are, as we said, for each symbol we get 2 elements, which is the real part and the imaginary part. And since we can process 4 values or 4 floats at once, we can compute 2 symbols at the same time. So if you can see here, it's the real part of RE1, so real part of the first symbol, and imaginary part of the first symbol. Also, the real part of the second symbol and the imaginary part of the second symbol. So computation in SIMD is done with two vectors. So in order to do a computation, we have to have two vectors of the same size, of course. And in this case, we had to do the square root. So to compute, for introduction, to compute the absolute value of estimation squared, the real part and imaginary part squared. Shortly, it is just the real part squared plus the imaginary part squared. So it's simple. It's very simple to implement in this case. So we just square each of the elements of the symbols, and then I wrote a function which shuffles this vector. So each element, instead of being A, B, C, D, it's B, A, and C, D. So in this case, we have imaginary part of the first symbol in the first position, the real part of the first symbol in second position, and so on. So imaginary part of the second, real part of the second. And if we add this to the square of each element, we get the channel estimation for each position. So channel estimation squared for the first symbol, second symbol, and second symbol respectively. Now there is another SIMD process, which is the multiplication of the original signal with this channel estimation squared for each symbol, of course. And also here below, we can see that the offset is being multiplied with the same for channel estimations. Now, for 16 QAM, as we said, the 4 bits are done in the optimized version, the optimized manner. So we do also we can get, so for each symbol, we get the 4 bits. And this process outputs 8 bits, sorry. So for 4 for each symbol and 2 symbols at the same time. So as we saw before on the first top left graph, we can see the log likelihood ratio levels. Also, so there are a lot of outliers here where the respective of the echo on the channel that is estimated is, and these create a lot of errors. On the bottom left, we have the equalized symbol of 16 QAM, and it is visible. Yeah, and on the right, we have the channel estimation in complex plot. So this was the without the modification, and now this one is the modified version. So we can see that the log likelihood ratio, which is the top left, the first graph, its shape resembles the channel estimation, which in itself has folds. And this is also to say that the outliers are taken care of because they are nullified by so their uncertainty is nullified by the near zero channel. Okay, and these are some laboratory results that we got for different cases. This is for the yellow ones that are the highlighted, and which is the version 2, V2, in comparison to the original version, or that is abbreviated orig, for different cases, which is additive white Gaussian noise, echo at 1 microsecond at 1 decibel, and typical urban scenario. So, and when so for 2 cases, one is for 16 QAM as well, and the one for 64. What is to be noted here is that the signal to noise ratio, which is the most right column, we can see that the highlighted one is we have need for a lower signal to noise ratio with respect to the original. And what is the most interesting is that for typical urban scenario, which is TU6, we can reach we can have a changing channel, meaning that the receiver can be moving and with different velocities. And we did also some tests, and we reached up to 130 kilometers an hour, which is very impressive because it's the speed limit in Italian highways. We also did the same thing with MCS 16, which is 64 QAM. And we also got some impressive results, but in this case, signal to noise ratio was infinite, so we could not have a moving receiver in this case. So this is some laboratory test video. So on the right, we have the received signal where there's a moving receiver, so the channel is changing. And on the left, there is the same signal, basically, but with the modification that was presented before. So, conclusions and future steps. So this work demonstrated the possibility for to lower the signal to noise ratio and correct the video reception. Also, the change with the parallel computing that the code was already written on. And for future work, it's to understand whether it can be useful to integrate this functionality to SRS-Terrain and therefore into the modem itself. So keeping in mind that this functionality is only for broadcast functionality, for broadcast reasons, applications. Thank you very much.